One more derivative test, that's the one.
Okay. All right. So here we go. So today we're learning about derivatives, and we're going to start by sketching a little curve. So this is section 2.1. If you want to give it a title, you can call it Definition of the Derivative.
How do you spell derivative? Good question.
D-E-R-I-V-A-T-I-V-E.
Appreciate it.
Derivative. Alright, so I just have a random curve sketched on the board. Everyone just draw a little sketch of this curve. Doesn't that look beautiful? And I'm going to put some points at certain spots. There. On this curve. Okay, so do y'all have a curve with 5 dots on it?
Mm-hmm.
Good. What I want you to do is I want you to sketch little tiny tangent lines to this curve at each of those dots. Now, I'm going to start you off just to show you what I mean by a little tiny tangent line. So not the full line, just a little segment of it. So I'm going to draw a little tangent line to this dot right here. Bam. Okay? So everyone take a minute and sketch little tangent lines at each of those dots. Okay, y'all have your 5 tangent lines?
Is that decaf?
It is. Yes.
Do you put like French vanilla in it?
I do.
You're like an open book with Bryce.
I am. Okay. So I'm going to put that one there. I'm going to put this one like that and this one like that, right?
Right.
That's a little tricky. This one actually goes right through the function. What? What? Okay. Tangent lines can cut right through a function. They do not have to just touch the edge and skip off. Technically, they often do, but they don't have to. The problem with tangent lines, or the misconception with tangent lines, is that you learn them normally when you learn circles. So when you learn tangent lines only in the context of circles, all the tangent lines are on the outside of the circle, right? They're all kind of they just touch this little one point and then they kind of skip off. So you kind of get that feeling for tangent lines, but they're allowed to cut right through. They don't have to just touch the edge and bounce off. Technically, the definition for a line that's tangent to a curve is the only requirement is that it shares the same slope as the curve at that point, the point of tangency. So all you need to do is sketch a little line that shares, so this one's not that great, but it needs to share the same slope as the curve at that point. Okay? Alright, so a tangent line is a line that shares the same slope as the curve at the point of tangency. Now, why do we care about little mini tangent lines and their slopes? Right? Okay, we're going somewhere with this. Alright, so we're just going to write a little layman definition of the derivative. Okay, so the derivative is the slope of the line tangent to a curve at any given point. And since, of course, the slope of that tangent line is equal to the slope of the function at that point, it would be the same as saying the derivative is the slope of the function at that point. All right, so because they're the same. So the derivative gives you the slope of the line tangent to a curve at any given point. Why do we care? Why are we spending an entire semester studying slopes of tangent lines? And why is this the basis for all differential calculus, which is the basis for like tons of applications? You have, economics and engineering and space exploration. How is all of this related to little tiny slopes of tangent lines? Well, what does a slope give you?
Rise over run.
It's rise over run is how you calculate slope, sure. Okay. And in other words, what does a slope represent? Someone said it. A what?
A rate.
A rate of change. A rate of change, right? A rate of change. Slope is a rate of change. And remember, calculus is the study of change, right? So, this calculus, the study of changing quantities, the study of changing functions, changing data, it's the study of change. The way that we analyze that is through slopes, which give you a rate of change. And let me put this in a simple context. Suppose this function represented sales for the last 10 years for some organization.
Coca-Cola.
Okay, so things are looking good for them, right? Yeah. Okay, so say they've got like daily sales records. So every day they've recorded their total sales for the day. They've got them for 10 years. So they've got 3,600 sales entries. So you're not going to go to your CEO or your chief financial officer or anyone like that and say, hey, here's the last 36,500 sales records, right? They're not going to want to look at them because it's just a big giant pile of data, right? Okay. So what we do instead is we take that data, it's entered into some sort of a system, and then it's modeled with a function. So we do, did you guys ever do regression in any of your math classes?
Probably.
Yeah.
Any regression?
Yeah.
Okay. Regression is where you take data and kind of find a function that fits it well, right? So anyway, so we do a regression on the data, you've modeled with an appropriate function, so now you have this lovely function that models all the sales data. Well, that's just great, and that's helpful in certain ways, but your head of your company is not going to want to know all of the data, and they're certainly not going to want to know the function that models it. What they are most interested in are the following pieces of information. When were sales increasing? When were sales decreasing? When did sales hit a low? When did they hit a high? When they switched from increasing to decreasing, right? When were they going up and then they switched to dropping, right? When were they increasing the fastest? When did they switch from increasing fast to slowing down and leveling off? All of these answers, or all these questions can be answered with
Derivatives.
or in other words,
Math.
slope.
Oh.
Slope,
Math.
right? Yeah, and math. They can all be answered with slope. Because if you look carefully, wherever this function is increasing, the slope is what?
Positive.
It's positive. And whenever the function is decreasing, the slope is
Negative.
negative. When we hit a max or a min, what's the slope?
0.
It's 0, right? So we can just, with this function, just pertaining to sales, we could find the derivative and make a derivative sine line, find all the zeros, we've got all our maxes and mins, and the signs will tell us where is it increasing, where is it decreasing, where is it increasing, right? And we'll know just from that sine line all the major things we need to know about that function. And then what your teachers can do, obviously, is just for the whole semester, we can just change the functions, right? Because there's all kinds of different functions to choose from, and then just apply different contexts to it and analyze, right? So there's all kinds of different contexts we can put a derivative into where we can analyze it. We're going to do most of this analysis kind of stuff in Chapter 3. Chapter 2, what we're about to start on, is just the nuts and bolts of how to find the derivatives of the major functions. Okay? So this chapter, the unit that we're about to embark on, is really more of a nuts and bolts. Kind of like when you're a kid, you've got to learn how to do basic arithmetic before you can start solving all these word problems about it, right? So you gotta learn nuts and bolts. So chapter 2, the one that we're about to start, is a nuts and bolts chapter of just how to find derivatives. Now, have you ever been in a class where the teacher taught you this really long, convoluted method for doing something, and then the next day said, hey, by the way, there's this like really short way to do it,
Which is
and
really stupid.
you're like, why didn't you tell us that one first?
Yeah.
Have you ever been, has anyone ever experienced this? It's usually in math, but it could be other places, right? Okay, well, we're gonna do it again, right?
Why?
Yay! Okay, so today we're gonna learn what's called the definition of the derivative. The definition of the derivative is the long way to find a derivative, okay? It's important. The reason it's important is because the only way to really understand what a derivative is to learn its definition. So once we learn these, and there's 3, once we learn the definitions, and we quiz on them tomorrow, then on Monday, we get to start doing all the short ways. Okay, so Monday you get to learn the shortcuts, and then you get to do shortcuts for the rest of the chapter. Does that make sense? And the rest of the semester. Okay, so one day on the long way. So I'm going to explain to you how we find a derivative. And I'm going to do it in a context of a curve. Okay. Now let me ask you this. Looking at these little tangent lines, they each have their own little slope, right? The slope of this line is 0. The slope of this line is some negative number, right? Like maybe, I don't know, -8, okay? Some negative number. So we've got these little individual slopes. Would you call these rates of change of this function, like the rate of change at this little spot, would you call that an average rate of change over an interval, or would you call it an instantaneous rate of change at one spot?
Instantaneous.
An instantaneous. A derivative gives you an instantaneous rate of change. The slope that you've learned all along, change in y over change in x, implies that there is a change in x, which means it's an average rate of change. It's over an interval. What we're going to learn now is an instantaneous rate of change. So let's pretend that we want to find the instantaneous rate of change at this point right here, which I'm going to call x, which is poor notation because I'm also going to call the function f of x. But anyway, that's okay. We're going to call the function of x, and I'm still going to call that spot x. Now, I'm going to call this spot another name, but I'm going to show you how we're going to figure it out.
Potato bread.
The difference from here to here, the distance between these two x values, I'm going to call delta x or h.
Ooh.
Okay? So you can either one. They both have meaning. Delta x or h. I'm going to go with h actually because it's more familiar to us. But anyway, delta x or h represents the distance between these two x values.
Right.
All right? So if this one is called x, what would I call this one?
X2.
Delta x minus x.
X
You're very close.
X subscript
The other one.
the other one. Y.
C.
X plus delta h. Delta x.
Do you all agree that if this is x and the distance here is h, that this would be x plus h?
Yeah, that's what I meant. I was
Okay.
kidding.
Oh, that's good. That was good. Okay. So, I gotta turn this around to keep track. Oh, good. We're right on. We're good. All right. So anyway, now let's talk about y values. If this is x, what's this y value?
What?
Okay, but in function notation.
F of x.
F of x. If this is x plus h, what would that y value be?
F of x.
F of x plus a.
F of what?
X plus
X plus h. F of x plus h, right? Plugging that x into the function. All right. So let's just connect. Now, if you're drawing, just be careful. You might not want to draw the next 3 or 4 things I draw because it's going to get really messy. Okay? All right. So I'm gonna connect these two lines with or these two dots with a line. We call this a secant line, all right? It's a line that connects two different spots on a function, all right? So suppose I asked you to tell me how to find the slope of the secant, which in other words is the average rate of change of f of x from x to x plus h. So, I want a formula to find the slope of that line. What's slope in general? How do you find
Rise
slope?
over run.
Rise over run. And what's another formula for slope?
Change in y over change in x.
That was beautiful. Change in y over change in x. So for this one, how would we write the change in y?
So f of x plus h minus f of x.
Over?
X plus h minus x.
So if we simplify, this just equals over h. Whoa.
This looks familiar.
Does this look familiar?
I have no idea what you're talking
I was in that weird math class, so I was like,
Does it look familiar? All these f of x plus h minus f of x's over h's that we've been making you do since chapter P, those were just slope formulas? What? They're just slope, right? So f of x plus h minus f of x over h is just the slope of the secant line through these 2 points, to any 2 x values separated by a distance of h. Alright, so we found the slope of the secant. I don't want the slope of the secant. I want the slope of the tangent. I want the slope at x. I don't want the slope through like these 2 points. I want the slope here. So would this slope be a really good approximation for that slope?
Negatory.
No. But let's see, what could I do to make it better? If I move this point down here, so I make my h a little bit smaller. So I'm going to just kind of move it in a little bit. And I draw a new secant line. Is that a better approximation?
Yeah, it's better.
Is it exact? No, it's still an approximation, right? It's better, but it's not great. So let's say I move the point a little bit closer. Move it in a little bit further. Making my h a little bit smaller. And I draw a new secant line through those 2. Is that better?
Yes, it's getting better.
Is it better? Is it exact?
It's infinitely off.
It's infinitely off. Yeah, it's infinitely off. So suppose I wanted the exact slope of the tangent, or in other words, the instantaneous rate of change. Well, let's see. If I want the actual slope at that point, what I'd want to do is take this point and move it so it's right all the way on top of that guy, right? If I take this point and move it so that it's right on top of the other one, what value is h approaching? Is it
0.
is h approaching x or is h approaching 0?
0.
H is approaching 0 because remember h represents the distance between these 2 points.
Right.
So if I take it's a beautiful L word.
Limit.
The limit,
Oh, I was guessing love.
that's also a good L word, but this one's good too. The limit as h approaches 0 of my slope function now I have an instantaneous rate of change. And this is the basis for differential calculus. Okay?
That's so smart that you taught us limits before you taught us this.
Wasn't that handy?
It was.
Handy.
I know. Okay, so what we're going to do right now is first we're going to write some notation, and then we're going to write down the three definitions of the derivative. I'm going to zoom in a little bit. Okay. So, notation. Notation. All right, so for y equals f of x. So you got some function y, which is a function, f of x. For y equals f of x, the derivative can be written as any of the following. The derivative of y can be written as y with a little apostrophe, and we call that y prime. All right, so that's like the quickest and easiest way to write the derivative is to write y prime. So if you see someone saying, oh, y prime is 2x plus 3, that means the derivative of y is the function 2x plus 3. All right, so y prime. You could also, same kind of notation but with a function, write f prime of x. You can also write dy dx. Now dy dx I like because it reminds me of the old slope formula you used to write when you were young. Delta y over delta x. Delta y delta x, what does delta represent?
Change.
Change, right? So delta y delta x represents the change in y over the change in x. This is what's talking about an average rate of change between two values, right? When there actually is a value of change. This dy dx is talking about the limit as the distance between, or the change in x approaches 0. And so what you get for dy dx, it's like delta y delta x, except it's implying that there is no change, it's instantaneous, that d. You'll see a lot of, well, let's just do the last one. You can also, for functions, if you want to use the dy dx kind of notation, you write d dx of f of x. D dx in front of anything means the derivative of that thing. Now the dx is, you'll see in, especially in college, I have a lot of professors that used to just write like the derivative of f. And they would just put df and just use the d as like a derivative operator, like just to say, all right, d means you're going to take that derivative. So you'll see that a lot, and that's fine. The dx, for the purposes we're using right now, is just informative to tell you that we are differentiating with respect to x, meaning that we're differentiating this guy, and by the way, the input variable is going to be x, all right, for our derivative. So that's all. But in the future, especially when we get into integrals, we will be treating these as actual fractions, and we'll be using, like, moving the dx around. So I always keep proper notation dy dx or d dx with the function. I don't just use a d. But you can, it just means it's like an operator. All right, so here we go. Does everyone understand that's notation? These all just mean derivative. Okay, just 4 ways of writing. All right, there are 3 definitions. The first one is the general definition of the derivative. And this yields a slope finding function. Meaning that your input, your whatever you're finding the derivative of will be a function, your output will also be a function. The derivative will also be a function, and what it does is it lets you find the slope at any point on that function. So it's like a function you can plug values into to get out slopes. So like on a function, the regular function, you plug in x's, you get out y values on the graph. For the derivative, you plug in x values, you get out slopes. So it's a slope finding function. All right, and here's your definition. So f prime of x is the limit as h approaches 0 of f of x plus h minus f of x over h. This should look familiar, because we've already done it today, but you've also done it in the past. And if you're still not good at those x plus h's, this is something you want to kind of get up to snuff before tomorrow, because you have a quiz on it tomorrow, right? So that's something you might want to work on. It's going to be all over your homework tonight. Okay, I'm gonna write down all three definitions and then we'll do examples. Okay, so that's the general definition of the derivative. Then we have an alternate or specific definition of the derivative. The alternate definition of the derivative actually gives you a slope at one specific value of x. So when you use the general derivative, you get out a slope finding function. Your answer will usually have x's in it. When you use the alternate definition, your answer is going to be a number. It's just going to be the slope at whatever x value you're interested in. There's two alternate definitions. The first one says f prime of c is the limit as h approaches 0 of f of c plus h minus f of c over h. Now, this and this are identical. What's the only thing that's different? The x's became c's. So instead of x's, you'll have numbers. So you'd have like f prime of 5, and then it would say you'd have the limit as h approaches 0 of f of 5 plus h minus f of 5 over h. You'll have a number, and then the output will be the slope at that number. The other alternate form, f prime of c, is the limit as x approaches c of f of x minus f of c over x minus c. Both of these are good, and you have to know all three. But if you get to choose, I personally like the bottom one the best. It's the easiest.
I like it too then.
But you would get the same answer.
The same answer, no matter what. Okay, so are you ready to try some? Dun, dun, dun. Here we go. We're going to start simple. Okay. We're going to find the derivative of y equals x squared.
That sounds hard.
Does it really sound hard?
No.
Okay. Let's say you don't get too much more basic than y equals x squared. All right, so I'm going to start you off by saying y prime equals, that would be our derivative, and I'm going to apply, now did it say the derivative of y equals x squared at x equals 6?
No.
No. When it doesn't give you an input value, it just wants the general derivative. So we're not looking for f prime of 6, we're looking for just f prime. Okay? Which means we're using the general derivative, so y prime equals, well, let's see. Oh, I didn't call it a function, I didn't call it f of x, is that okay? Can we still
Yeah.
do it? Yeah, so it's the same kind of thing. So the limit as h approaches 0, don't forget your limit of, how would I do f of x plus h for x squared? Would that be x squared plus h? X squared plus h.
No.
Negatory.
X plus H parentheses squared.
But this is so easy, I just cross off the x's and the answer is 1.
Math isn't easy.
Math isn't easy, if it's easy, it's probably wrong. Okay, yeah, it's not x squared plus h. When you're not sure, remember, replace the x in your function with a parenthesis, and then put the x plus h inside the parenthesis. Alright, so rewrite your function with a parenthesis for an x, and then put the x plus h inside of it. Do you all understand that?
Yeah.
Okay. Alright, what I want you all to do now is take a minute and finish this. You can talk to each other.
We don't like talking.
You don't want it?
I hate those.
Never worry about my feelings.
Two x plus h. You get 2x plus h.
That H you just received. And the page is there.
That's so easy. I see destroyed 45 times the amount of this.
Yeah, no.
You can just call me the Knicks.
You like SAT score on top side.
I got H.
Yeah.
It's better.
I did not pay me.
That could be.
32 H.
I got
31.
He's good. Thanks, guys. You haven't made that much money. Sure, he's
X plus H. Hey, we said that at the same time. Wait. Holy crap, I actually sold
Is that
this.
wrong?
I'm hearing a lot of incorrect answers, and I know why they're incorrect.
Oh, well, can you tell us?
The bad
algebra. Would you like me to tell you?
Guess what
Yeah.
PAs?
Too much.
So, of course, this is a
Oh, yeah,
limit,
you're right.
so what's the next thing I'm gonna make sure I write on the next line? Limit as h approaches 0. I'm gonna square this out. Did y'all square that out?
Yeah.
Okay. X squared plus 2xh plus h squared minus x squared over h. Everyone get that?
Yeah.
Good, okay. So now, what happens next?
Take out an H.
Cancel what?
Simplify.
The x squared. If you do it right, every term without an h in it will drop out. Right, so we are left with 2xh plus h squared over h. I always used to cancel right from here, but I'm seeing so much bad canceling on tests and quizzes that I'm going to require you guys factor it out. I want you guys to get in good habits. We're going to do good canceling habits. So if you can't factor it out of every single term, you don't get to cancel it. Alright? Every term, or you don't get to do it. Alright, so now h is gone. So what's my answer?
2x.
It's just 2.
You see, nobody likes you. That's why you keep going.
Okay.
Well,
Those of you who got
H is
2x plus
0.
h, what did you miss?
The fact that H is approaching 0.
You didn't plug your
I
0
went
in
on
for your
chasing when I was
h,
wearing long
right?
sleeves.
And the easiest way to miss that is if you fail to write your limit statements, right? Okay, alright. Now, here's what that means. So if I have the graph of y equals x squared, so here's the graph. And I just have regular old function values on the graph of y equals x squared. So let's say like f of 1 is 1, f of 2 is 4, f of 3 is 9, right? Kind of stuff. F of 0 is 0. Alright, So that's just my normal, if I had f of x was x squared. What we just found was that f prime of x was 2x. Well, what that's saying is, if I said f prime of 1 is 2, f prime of 2 is 4, f prime of 3 is 6, these are not values on this graph. Well, one of them is, but anyway. They're not values on the graph. What do these numbers represent? Slopes. So does it make sense that this is 2, but then this slope would be 4, and then this slope would be 6, that they're getting steeper like that?
Yeah.
Ooh, let's do some negatives. How about f prime of negative 2? That would be
Positive slope, negative slope.
negative 4, because I'm plugging into my derivative, right? So my slope over here at negative 2 would be negative 4. Does it make sense that for your slope, whenever x is negative, it's negative? Why?
Because you have a negative slope.
How do you know you have a negative slope over here?
It's going down.
Because the graph is going down, right? So whenever the graph is going down, the slope would better be negative. Whenever the graph's going up, the slope would better be positive. If I were to graph y equals 2x, does this graph look anything like this graph? And the graph of the derivative and the graph of the function will never ever look alike. They will relate in that whenever this guy's negative, this one's going down, and whenever this guy's positive, this one's going up. But apart from that, they're not going to look alike. Okay, so never try to make them look alike. They will always look different. They relate, but they will look different. Okay, let's use some alternate stuff. All right, example. If f of x equals square root of x, find f prime of 9. So if f of x is the square root of x, find f prime of 9. All right, now we want the actual slope at a number. You can find this by finding the general derivative and then just plugging the number in, right? That's totally fine. And if you need a whole bunch of slopes on a function, that's the way to do it. But if you only need one slope at one point, then using the alternate definitions is always a little bit faster. So, do you want to try it start to finish, or do you want me to help you get it set up first?
Let's have you help.
Let's have us help me help you. Okay. All right, I'll help you just set it up. Which one do you want to use, the top one or the bottom?
Bottom.
Oh, okay. That was overwhelming. All right. So here we go. Our C is what for this problem?
9.
So if f prime of 9 equals, oh my gosh, it's another limit, as x approaches 9. There are no h's in this one. X approaches 9 of f of x. What's f of x? Square root of x. What's f of 9?
3.
It's 3 over x minus 9. F of x minus f of 9 over x minus 9.
Multiply by the conjugate.
All right, you could do conjugate, you could factor the bottom. There's lots of ways to do this. However you want to do it is fine. Go ahead and do it.
Yeah, I would be back to the bottom if it's just a normal x, not x.
What's the square root of x?
Oh, it's so smart.
Isn't that
guys.
cute? I know.
Goodness.
What is this word?
It's the square root of x minus 3 and then the square root of x. That's goodness, I wish I was just like, goodness. She's just so smart. So jelly of Miss Price right now.
It's good you're getting all this on tape.
6.
Yeah. Multiply by the conjugate, get x times number, that's 9 times number. We can't do that, not conjugate 1.
Where did you get your
Square root of x will be 3.
take that 6?
Yeah. And then you get,
Yeah, but then if you plug in 9, so what if 9 is some people no, because it's a 3, because that's not minus. It's plus.
You guys already done? Alright, what did you guys do? Did you multiply by the conjugate or did you factor?
multiply by the
Conjugate? Okay.
How would you factor it? Because it's not.
This would be root x plus 3, root x minus 3.
That's why she was so smart.
It's 1 over
No,
root
it's
x
just
plus
because someone
3.
else has taught me that. Okay. So I multiply by the conjugate. I rewrite my limit statement. What does the top become?
X minus 9.
X minus 9. Should I multiply out the bottom?
No.
No. That would be silly. What do?
Cancel out.
Cancel out the common factors. Now can I plug in?
Yes.
And what do you get?
1 over 6%.
1/6. So what that is saying is the slope of the line tangent to square root of x when x is 9 is 1/6. 1/6. Which makes sense. It's a real shallow slope because it's kind of leveling off over there, right? Still positive, but shallow. Okay, let's take it up a little notch. And I'll tell you about your quiz too. But first we're going to do one more example.
Wait, so you have the tests graded, but you're withholding them from us?
They're not all graded yet. They're close. I'm almost done.
Third period graded?
I never grade by class. I grade by version. So
So the
I've
correct
graded
version?
2 versions so far.
Did you grade the version without the mistake?
I've graded, I have no idea. I've just graded 2 versions. Okay, write the equation of the line tangent to f of x equals 2x cubed at x equals 1.
Yeah, I'm gonna need some help on this one.
Cause you're done?
Yeah.
Okay, write the equation of the line tangent to the function f of x equals 2x cubed at x equals 1. What 2 things do you need to write an equation of a tangent line? A point and a slope, right? What the 2 things you need to write an equation of any line? Same again.
Point and a rate.
Point and a slope, right? Point and a slope. Okay, so this is no different. So we need a point. Well, what would our x value be?
1.
And how would I find the y value? So what's my y value? 2. Alright, that was easy. Now all I need is a slope. How do I find slope now?
Your formula. Did you?
I use the derivative, right? I use the derivative. So I need f prime of 1, because that would equal my slope at x equals 1. So everyone take a second, find f prime of 1, and then see if you can write the equation of the tangent line. Oh no. We're going to have to factor a what?
Cube root.
Difference of cubes.
So same opposite.
So,
Plus x.
No, x minus 1.
Always positive.
Same.
Opposite, always positive. Plus 1.
what do you know this factor is going to be?
X minus one.
Yeah, you get it because you know it's same as the bottom, right? So you always write the cube root and the cube root, take the first term and square it, take the last term and square it, multiply for the middle, signs go same, opposite, always positive. All right, keep going. All right, for time, I'm going to finish this up. What's the limit? 6. So that means that our slope is 6. Our point is 1, 2. Please, please get in the habit of learning point slope form. Because you're always going to have a point and a slope, and if you have to sit there and convert this to slope intercept by calculating what b is and then plugging them into y equals mx plus b, it's going to take you more time and leave you open for more error than if you can just plug into point slope. There's going to be so many tangent lines all year long, so I really encourage you to learn point slope. It takes 2 seconds, there's no calculations, you're just done. Now, quiz tomorrow, 3 questions. First question, general definition of a derivative.
That's a writing
Okay.
question, no math.
No, you have to actually use it. You'll have to use it. Second question will involve one of the alternate definitions of a derivative,
Third question, when is this?
but it is very similar to a problem in your homework tonight. So I would encourage you to make sure you can do all of your homework because it's not exactly straightforward. It's fun though. And then the third one is equation of a tangent. So you can use whatever method you want to find the slope. Does anyone in here know the shortcut method